Alright, let's go. Number 10. The Grandfather Paradox. You already know the story. Time traveler goes back, kills their own grandfather, wipes themselves from history. Cute science fiction. Except in 1991, David Deutsch at Oxford wasn't thinking about science fiction. He was working on quantum computation, trying to prove what quantum systems could calculate that classical ones could not, and he needed to work out how the mathematics of quantum mechanics behaved in curved spacetime. Standard general relativity does something uncomfortable here. Einstein's field equations do not explicitly forbid closed time-like curves, trajectories that loop back on themselves in time. Multiple exact solutions permit them, and yet every classical intuition demands that cause must precede effect. The equations say one thing. Physics teachers say another. Deutsch tried to reconcile the two. He couldn't. His 1991 paper, Quantum Mechanics Near Closed Time-like Lines, in Physical Review D, Volume 44, page 3197, showed that quantum mechanics can accommodate time loops, but only by forcing a very specific mathematical trick. Reality selects a fixed-point solution. Any scenario that would produce a contradiction is replaced by a probabilistic mixture that stays self-consistent. Physicists tried to escape it. Stephen Hawking proposed his chronology protection conjecture in 1992. Some unknown physical mechanism must destroy any wormhole attempting to become a time machine. He never proved it. Igor Novikov argued that the universe simply forbids inconsistent histories, offering no mechanism at all. Many worlds theorists suggested the killer just enters a branched timeline. Untestable. Others argued we should just declare closed time-like curves unphysical. But the math does not care what we declare. If Deutsch is right, your identity is not fixed by your choices. It is filtered by consistency. Every version of you that could have contradicted itself was never allowed to exist in the first place. The you reading this sentence is what survived the filter. What enforces that filter? And how would you ever notice if it was operating on you right now? The math permits time loops. It does not tell us what happens inside one. Number 9. Gödel's rotating universe. In 1949, Kurt Gödel, the logician who had already broken mathematics with his incompleteness theorems, was living at the Institute for Advanced Study in Princeton, taking daily walks with his best friend Albert Einstein. For Einstein's 70th birthday, Gödel wanted a gift, not a book, not a painting. He wanted to give Einstein a solution to his own field equations that Einstein had never noticed. The standard understanding at the time was that general relativity described a universe in which time flowed forward, cleanly, everywhere. Solutions describing expansion existed. Solutions describing black holes existed. But time itself was assumed to be well-behaved, a global parameter that any observer could agree on. Gödel found something else. His paper, an example of a new type of cosmological solution of Einstein's field equations of gravitation, published in Reviews of Modern Physics, Volume 21, page 447, in 1949, described a rotating universe. In it, every point in spacetime had closed time-like curves passing through it. Travel far enough in a rotating Gödel cosmos, and you arrive at your own past. Not metaphorically, mathematically. Physicists tried to dismiss it. First argument, our universe doesn't rotate, so the solution is irrelevant. Except the equations don't care whether it describes our cosmos. They only need to describe a possible one. And if a possible universe permits time loops, general relativity itself permits time loops. Second argument, the energy conditions are exotic. Except Gödel's solution uses ordinary pressureless dust, not exotic matter. Third argument, no observer would ever actually traverse the loop, except the trajectory is time-like. A real observer could, in principle, follow it. Einstein read the paper. He wrote a careful reply. He did not say Gödel was wrong. He said the problem of time in his own theory was, in his words, not yet settled. If a mathematician can hand you a universe where the past is a location you can walk to, what does that say about the theory we use to describe this one? One rotating universe was hypothetical. The next attempt at consistency was more ambitious. Number 8. The Novikov self-consistency principle. Russian astrophysicist Igor Novikov spent the 1970s and 80s studying black hole thermodynamics, routine, respected work on how matter behaves near event horizons. In the late 1980s, working alongside Kip Thorne, John Friedman, and Michael Morris at Caltech, he turned to a harder question. If general relativity permits time machines, even in principle, what mathematical rules would prevent them from producing outright contradictions? The classical prediction was pessimistic. A time machine plus free will equals paradox, the grandfather scenario. The letter that tells you not to send it, the bullet that stops the gun that fires it. Each one seemed to demand that either time travel is impossible or logic breaks. Novikov proposed a third option. In a 1990 paper co-authored with Friedman, Morris, Thorne, Echeverria, Klinkhammer, and Yurtsever, in Physical Review D, Volume 42, page 1915, the group formalized what became the Novikov self-consistency principle. Any events allowed to occur via time travel must already be self-consistent. You cannot kill your grandfather because something, a stumble, a misfire, a coincidence, will always prevent it. The universe does not permit inconsistent histories. Physicists have picked at it for 35 years. Objection 1. It violates free will. Novikov's reply: free will was never guaranteed by physics in the first place. Objection 2. It offers no mechanism, only a rule. True. It says what happens without saying why. Objection 3. Probabilistic scenarios seem to require improbable coincidences to enforce consistency. Deutsch's quantum extension resolved this by allowing mixed states. Objection 4. It makes no falsifiable prediction. Also true. It cannot be tested until someone builds a time machine. Notice what the principle does not do. It does not prevent time travel. It only forbids contradictions. Under Novikov's rule, you can go back. You simply cannot change anything you did not already do, meaning every choice you have ever made may be the only choice you were ever allowed to make. Does that feel like freedom? A rule that forbids contradictions still allows something stranger to slip through. Number 7. The Bootstrap Paradox. The idea entered serious physics through discussions of self-consistent time loops in the 1990s, but the philosophical setup is older. The question researchers kept coming back to was mundane. If the Novikov principle is correct, and closed time-like curves are self-consistent, what kinds of objects and information can exist inside one of those loops? The standard assumption was that everything must have an origin. Every book was written, every idea was thought, every particle was created. Causality means chains of cause and effect that begin somewhere. The bootstrap scenarios broke that assumption. Consider the version philosopher David Lewis analyzed in his 1976 paper, The Paradoxes of Time Travel, in American Philosophical Quarterly, Volume 13, page 145. An older version of you hands your younger self a notebook containing the complete proof of a difficult theorem. Your younger self studies it, memorizes it, and decades later delivers the same notebook to the same younger self at the same moment. The theorem is proved. The notebook exists. Nobody ever wrote it. Every explanation collapses. Attempt 1. Someone must have originally written it. But under strict self-consistency, no such person exists anywhere in the timeline. Attempt 2. The information is somehow created inside the loop by physical processes. But information theory forbids the spontaneous appearance of structured, meaningful content without a source. Attempt 3. It must violate conservation of some quantity, and therefore cannot happen. Yet nothing in general relativity or quantum mechanics forbids the configuration. Attempt 4. It must be an illusion, a coincidence, but the notebook contains a real proof. The proof works. The uncomfortable conclusion is that if closed time-like curves exist, information can exist with no origin, structured knowledge with no author, a theorem no one discovered, a song no one wrote. You believe your memories came from experiences. You believe your ideas came from thinking. If loops in time are real, those beliefs are not guaranteed. Some fragment of what you think of as yourself may have no first cause at all. Information without origin is unsettling. A physical machine to reach the past is worse. Number 6. Kip Thorne's traversable wormhole. In 1985, astronomer Carl Sagan was writing his novel Contact. He wanted his protagonist to travel across interstellar distances in a physically plausible way, so he asked his friend Kip Thorne at Caltech to check the physics. Thorne, then one of the world's leading general relativists, took the question seriously, perhaps more seriously than Sagan intended. The standard understanding was that wormholes, if they existed at all, were unstable curiosities. Einstein-Rosen bridges, the original wormhole solutions from 1935, collapse the instant anything tries to pass through them. Any object entering one would be crushed before emerging. Interstellar travel through a wormhole was considered mathematically impossible. Thorne proved otherwise. His 1988 paper with Michael Morris and Ulvi Yurtsever, Wormholes, Time Machines, and the Weak Energy Condition, in Physical Review Letters, Volume 61, page 1446, showed that general relativity does permit a stable, traversable wormhole. It requires only one ingredient, matter with negative energy density, holding the throat open, and any such wormhole, if manipulated correctly, becomes a time machine. Every objection has been examined. First, negative energy is impossible. Except the Casimir effect demonstrably produces regions of negative energy density in the laboratory, small amounts but non-zero. Second, quantum effects would destroy the wormhole before it could function as a time machine. This is Hawking's chronology protection conjecture. Never proven, and Thorne's own follow-up work suggested the divergences might be tamed. Third, it requires astronomical amounts of exotic matter. Currently, yes, but currently impossible is not the same as forbidden. The paper has never been refuted. The math has been checked by 3 generations of physicists. It sits in the peer-reviewed literature, unresolved, waiting on a single if. If the exotic matter exists in usable quantity, the door opens, which means the door to your own past is not closed by physics. It is closed only by engineering. And engineering, unlike physics, has a habit of catching up. How long exactly until it does? One wormhole design needs exotic matter. A different design needs only spin. Number 5. The Tipler Cylinder. In the early 1970s, a graduate student named Frank Tipler at the University of Maryland was working on a fairly conventional problem in general relativity, investigating whether certain rotating solutions to Einstein's equations could produce physically meaningful predictions. He was extending earlier work by Willem van Stockum from 1937 on infinite rotating dust cylinders, checking what fell out of the mathematics. The prediction from standard relativity was straightforward. Rotating masses drag spacetime around them, the frame dragging effect confirmed by Gravity Probe B in 2011. In ordinary situations, that dragging is tiny, negligible outside precision experiments. Tipler found a case where it was not tiny at all. His 1974 paper, Rotating Cylinders and the Possibility of Global Causality Violation, in Physical Review D, Volume 9, page 2203, demonstrated that an infinitely long cylinder of dense matter, rotating fast enough, drags spacetime severely enough near its surface to produce closed time-like curves. Travel around such a cylinder along the right path, and you return to a moment before you started. Physicists have spent 50 years trying to bury it. Objection 1. Nothing infinite exists. True. But Tipler and later authors showed that finite cylinders of sufficient length should still produce local time loops. The infinity was mathematical convenience, not physical necessity. Objection 2. The required density and rotation speed exceed anything achievable. Currently correct, but not a proof of impossibility. Objection 3. The cylinder would collapse into a black hole before achieving the required parameters. Detailed stability analyses have gone both ways. Objection 4. Hawking's chronology protection would prevent the causality violation from actually manifesting. Still unproven, 52 years later. The equations, again, do not care what we would prefer. They describe an object that could in principle be built. A cosmic drill, spinning fast enough to twist time itself into a loop. If the universe permits such a machine, the past is not a memory. It is a place with an address. Rotating spacetime is theoretical. The next item has been observed in laboratories. Number 4. The delayed choice quantum eraser. In 1999, physicists Yoonho Kim, Rong Yu, Sergei Koshutz, Yenhua She, and Marlon Scully at the University of Maryland were running a standard test of quantum entanglement. Their goal was to extend existing quantum eraser experiments to see if the timing of a measurement could be pushed further apart than anyone had tried before. It was a technical refinement, not a search for weirdness. The prediction from standard quantum mechanics was already strange. If you measure which slit a particle passes through, it behaves like a particle. If you don't measure, it behaves like a wave. Fine, but cause always precedes effect. The choice must come first. Their apparatus violated that assumption. In their 2000 paper, Delayed Choice Quantum Eraser, in Physical Review Letters, Volume 84, page 1, they showed that a measurement decision made after a photon had already been detected still determined whether that earlier detection showed wave or particle behavior. The order of events was only rearranged when the data was correlated afterwards. But the correlation was undeniable, and it has been reproduced in laboratories around the world for a quarter century. Every interpretation strains to explain it. Copenhagen interpretation: no violation, just a rejection of realism about the past. Many worlds: no violation, all outcomes occur in parallel branches. Consistent histories: no violation, only certain narrative sequences are allowed. Retrocausal interpretations, developed by physicists like Hall Price, take the result at face value. The future does influence the past. None of these is provably correct. All of them require abandoning some intuition that physicists once considered non-negotiable. Note what makes this different from every other item on this list. This is not theory. This is not mathematics on a chalkboard. This is a laboratory experiment. It has been replicated. It works. Which means, somewhere in the fine structure of reality, the past is being edited. Every time the experiment runs. Your past may be less fixed than you think. That was quantum mechanics interfering with time. This next one is relativity doing it plainly. Number 3. The twin paradox. In 1905, a 26-year-old patent clerk named Albert Einstein was working through the implications of his new theory of special relativity. He was not looking for paradoxes. He was trying to make electromagnetism and mechanics agree with each other, a technical problem that had bothered physicists for 2 decades. The standard prediction of Newtonian physics was simple: time is the same for everyone. 2 identical clocks, however moved, however separated, will always agree when brought back together. Einstein's equations said no. The paradox was named and sharpened in 1911 by French physicist Paul Langevin in a paper presented at the Bologna Philosophy Congress. 2 twins, identical at birth. One stays on Earth, the other boards a spacecraft, travels at close to the speed of light to a distant star, and returns. When they reunite, the traveling twin is measurably younger. Not metaphorically, not perceived, physically younger. The atoms of her body have aged less. The resolution took decades to nail down and still trips up trained physicists. Naive objection: relativity says motion is symmetric, so each twin should see the other as younger. Contradiction: wrong. Only the traveling twin undergoes acceleration, breaking the symmetry. Second objection: general relativity is required to properly handle the acceleration phase. Not quite. Special relativity handles it in the traveling twin's non-inertial frame with careful accounting. Third objection: it has never actually been observed. False. Joseph Haffel and Richard Keating flew atomic clocks around the Earth in 1971, published their results in Science, Volume 177, in 1972, and measured the predicted time difference to within a few nanoseconds. GPS satellites require the correction every second, or their positions drift by kilometers per day. The paradox is not really a paradox anymore. It is a well-tested feature of reality. And that is what makes it disturbing. 2 people who lived through the same stretch of the universe end up different ages. Time is not shared. It is personal. Your seconds are not the same as anyone else's. Different ages from the same starting point. Now what if the future could visit the past? Number 2. The time traveler question. In 2009, Stephen Hawking, then 67 years old and deep into what would be his final decade of public work, was preparing a documentary on time travel for the Discovery Channel. He wanted a single, elegant experiment, not a mathematical proof, not a thought experiment, an empirical test anyone could evaluate. The prediction was based on a straightforward argument physicists had discussed for decades. If time travel to the past is ever possible for our species, even millions of years in the future, then future humans, or whatever we become, should have the means and the curiosity to visit interesting moments in history. Yet in all of documented human experience, no verifiable evidence of such visitors has ever been recorded. This is the temporal cousin of Enrico Fermi's famous question about aliens: where is everybody? Hawking's version was cleaner than Fermi's. On June 28, 2009, at Gonville and Caius College, Cambridge, he hosted a party. Champagne, canapés, balloons that read "Welcome, Time Travelers." He sent no invitations in advance. He publicized the party's exact time, location, and coordinates only after it had ended, in a note that would later be discussed in his book The Grand Design. The logic was ruthless. Any time traveler from any future era could have read the announcement and shown up on the day. He waited. No one arrived. Every explanation offered has holes. Explanation 1: time travel is impossible. Consistent with the result, but not proven by it. Explanation 2: time travelers avoid drawing attention. Then why would none arrive privately? Explanation 3: future humans have no interest in visiting past parties. Statistically implausible over cosmic timescales. Explanation 4: under the many worlds interpretation, time travelers went to different branches. Untestable. Explanation 5: they came, and something prevents us from remembering. Unfalsifiable, therefore unscientific. Hawking's own conclusion was cautious. He described the experiment as empirical evidence that time travel to the past is not possible for our descendants, not a proof. Evidence. Which leaves the question sharper than before. Not whether the future exists, whether the future is choosing, right now, not to visit. Every paradox so far has rested on one bedrock. The bedrock itself is now in question. Number 1. The unresolved status of causality itself. Every item on this list has quietly assumed one thing, that causality is a real, fundamental feature of reality, something the universe is actually built on. In the last 30 years, a growing number of physicists have started to question that assumption. They were not trying to overthrow causality. Most of them were working on ordinary problems in quantum gravity, trying to reconcile general relativity with quantum mechanics, and discovering that causality seems to be the first thing that breaks. The standard assumption of classical physics was simple. Cause precedes effect, everywhere, always, without exception. Newton assumed it, Maxwell assumed it. Even Einstein, who overturned so much, kept it. The bedrock has cracked. In a 2012 paper, Quantum Correlations with No Causal Order, in Nature Communications Volume 3, Article 1092, physicists Eugen Oreshkov, Fabio Costa, and Czaslaw Bruckner at the University of Vienna proved a theorem showing that quantum mechanics permits what they called processes with indefinite causal order. Two events, A and B, in which it is genuinely undefined whether A caused B or B caused A. Not unknown. Undefined. Their framework has since been experimentally realized in optical laboratories in Vienna, Queensland, and Hefei. Every attempt to explain it away runs aground. Objection 1. It is a mathematical artifact of the formalism. The experiments say otherwise. Objection 2. Some hidden classical order underlies it. Bell-type inequalities have ruled that out for the specific setups tested. Objection 3. Causality is preserved at a deeper level we cannot yet access. Possibly true, but currently unverified. Objection 4. The ordering just depends on the observer's frame. Special relativity permits this for space-like separated events, but the Vienna results go further. The events they describe are not merely order ambiguous, they are orderless. Every resolution proposed on this list, self-consistency, many worlds branching, chronology protection, is a patch, not a proof. Physics has no confirmed answer to whether cause must always precede effect. The math does not forbid it. It just hasn't happened yet. Or has it, and we simply can't remember. 10 paradoxes. 10 holes in the floor of a discipline that likes to think of itself as complete. Each one sits not at the edges of knowledge, but at the center of our most tested, most trusted theories. General relativity permits the machines. Quantum mechanics permits the interference. The equations do not warn us. They simply describe what is possible. The universe is not confused. We are. The order you believe your memories occurred in has never been proven. It has only been assumed. If you want to see more videos like this, click the video on screen now.